Hey, have you ever committed crimes in math out of curiosity? Like plugging negative numbers into area formulas, or plugging r greater than 1 in geometric series formula? You know, just to see what happens. Oftentimes, this ends up with you noticing why you're not allowed to do such a thing. For example, in geometric series, if you plug in r equal to 2 for instance, you'll immediately notice that this left side blows up to infinity, so it does not make sense to add them all up. And this does help you understand why there should be boundaries for substitutions. However, something much more peculiar could happen. Consider a unit square in the coordinate plane, with its sides parallel to the x and y axis, and with its vertices on the integer coordinate points. Then scale it up n times from the origin, and count the number of points with integer coordinates inside and on the boundary of this resulting n by n square. By the way, mathematicians call these integer coordinate points as lattice points, so we're gonna go with that. Well, there are n plus 1 lattice points along each side, so the total number of lattice points should be n plus 1 squared, right? Let's denote this by R of n, the number of lattice points in the n by n square. Now, what if you replace n with negative n in this formula? Well, you'll get this. So, where does this number n minus 1 squared appear in our picture? Look for a second, and you'll see that it is the number of lattice points that are strictly inside the n by n square. So in this case, plugging positive numbers into the formula counts the number of lattice points on the boundary and the interior of the square, while plugging negative numbers count the lattice points that are strictly inside the square. Neat, right? But what you just saw is not a coincidence. The same is true for any closed polygon. It doesn't even need to be on the plane. Or even any three-dimensional convex polytope. As long as all the vertices are lattice points, plugging negative numbers just removes the boundary. This is called Ehrhart Macdonald reciprocity. Well, this Macdonald is spelled with an M-A-C Mac, and the statement goes like this. Let P be any d-dimensional lattice polytope. Here, a polytope is a generalization of a convex polygon into higher dimensions. So a one-dimensional polytope is a segment, a two-dimensional polytope is a convex polygon, like a triangle or a square, and a three-dimensional polytope is a three-dimensional solid, whose faces are made out of convex polygons. For example, tetrahedrons, dodecahedrons, all those things are three-dimensional polytopes. And when we put the adjective lattice in front of the word polytope, it just means that all the vertices are lattice points. For any positive integer n, let R of n be the number of lattice points in n times p, which is the polytope you get from scaling p n times from the origin. Then, R of n agrees with the polynomial of n for all positive integers n, and more interestingly, if you replace n with negative n, you get the number of lattice points in the interior of n times p times plus or minus 1 depending on the dimension. So proving this requires two parts. One is geometry and the other is counting. But the theme of this video is on counting, and more specifically, it is about how so-called generating functions are very natural things to consider and why they are actually helpful in solving counting problems. Unfortunately, these objects are usually introduced without any motivation whatsoever, but I tried my best in this video to show you why they are actually natural. So this video is gonna go in 4 sections. The yellow sections, 1 and 3, are about generating functions, and the white sections, 2 and 4, are about proving the Ehrhart Macdonald reciprocity that we just talked about. Well, unfortunately, since we are gonna ignore the geometry part, we'll only be able to prove it for all polygons in the plane and all so-called simplices. But all of the ideas in the counting part of the proof will actually be present in this video. Also, don't worry if you're not familiar with higher dimensions. About 98% of this video will not go beyond 3D. So, without further ado, let's dive in. Before tackling our lattice problem, consider this little problem first, which is pretty famous, so you probably have heard of it. But nonetheless, the way we will solve it will give us the technique that we need to handle the Macdonald problem. Suppose you have an infinite number of identical 1x1 squares and identical 1x2 rectangles. Let's say f of n is the number of ways to form 1x n rectangle. For example, f of 1 is 1 because you only have one way to create the 1x1 rectangle. And then f of 2 is 2 because you can either use two 1x1 rectangles or just one 1x2 rectangles. Similarly, you can see that f of 3 is 3, f of 4 is 5, and so on. The question is simple. What is f of n? You might even notice that these are already Fibonacci numbers, and we'll get into that later. Okay, the way we are gonna do this may look weird at first, but in the end, everything will make sense, promise. Think of a bag consisting of all possible tilings over all possible values of n. So it contains an infinite amount of tilings that we can make using our tiles. Each tiling in this bag will be described as a string of symbols, encoding each 1x1 rectangle with an x and each 1x2 rectangle with a y. For example, this tiling right here will be written as xxyx, and this tiling right here will be written as xyxxyyx. We'll also include the empty tiling with no tiles at all, and we'll name it with the symbol 1. Okay, here is the weird part. We'll think of these symbols as if they're multiplied with each other, and then add up all the resulting products in our bag. So, our bag now looks like an algebraic expression of x's and y's, which we'll denote by b of xy. Okay, for those of you former folks out there who likes things to be more rigorous, these multiplication and additions are just formula operations, meaning that we're only interested in their usual properties. To be specific, we're working on this ring, the ring of power series generated by x and y. If you don't know what that means, don't worry. Just think of them as ordinary addition and multiplication, and this will work for understanding the main idea. Okay, what we want to do is to group the expressions in our bag corresponding to the total length of the tiles they represent. For example, we want these 5 expressions to be grouped together because they all represent the tiling of a 1x4 rectangle. How can we do that? Well, by thinking of these symbols as if they're multiplied, we can simply substitute x equal to z and y equal to z squared. Then, all of these products will become one symbol, z to the power of 4. It is pretty clear that this substitution will change an expression representing a tiling of length n into z to the power of n. Now, remember the plus signs that we put between our expressions. Therefore, we can add up all the equal terms, so the coefficient of z to the power of n in the resulting expression will be the number of tilings of length n. Therefore, if we denote our bag with b of xy, then b of z squared is just a power series in which the coefficient of z to the power of n equals f of n, which is the number of tilings we wanted to count. In summary, what we did is this. First, we considered the bag of all possible tilings. Second, we enriched our bag with an algebraic structure, transforming it into an algebraic expression, b of xy. This is almost like waving a magic wand on a pile of tilings. Personally, I like to think of this step as turning our tilings into little pets that listen to what you say. And third, we substitute x equal to z and y equal to z squared, and let the algebra do the grouping for us. This makes b of z squared to be this expression. Bringing up the magic analogy again, this step is like telling your little pets to find their partners according to their length. When I first encountered this kind of idea, my mind was genuinely blown. I mean, this symbol z right here doesn't even have a meaning. It doesn't represent anything. It's not a number. It's just there, a meaningless symbol following the algebraic rules. Oh, by the way, these symbols that exist solely for the sake of algebra and that doesn't represent anything are called indeterminates. And this b of z squared is called a generating function. In fact, this magical idea of grouping the terms together using algebra is not even the full strength of these generating functions. Let's see what they are actually capable of. From this series, we cannot directly compute f of n yet. To actually get f of n, we need to find b of z squared in a different way so that we can equate the coefficients. For this, let's go back to b of xy. Notice that the terms of b of xy fall into three categories: expression starting with an x, expression starting with a y, and the empty string 1. From the sum of all expressions starting with x, you can factor the x out. What's left inside? Take a second to think about it. The answer is b of xy itself. Of course, we can append anything behind the x that we have just factored out. Therefore, what is left should be everything. With this idea, we can rewrite b of xy as 1 plus x times b of xy plus y times b of xy. And if we rearrange this and solve for b of xy, we'll get this. Again, for those former folks out there, this fraction merely means the multiplicative inverse of b of xy in our ring of power series in x and y. You can actually prove that these power series with non-zero constant term always have a multiplicative inverse, but I don't want to prove it in this video. Okay, let's go back. Now, to find b of z squared, we simply substitute x equal to z and y equal to z squared. And there we go. We have finally solved our problem. What? Is it not already solved? Well, if you want the explicit formula, you just need to find the coefficient of z to the power of n in this fraction. And if you know some Taylor series stuff in calculus, I'm sure you can do it. I'm not gonna go into details, so... Looking back at what we did, this strong ability to calculate the explicit formula comes from this relation, which is obtained by considering all possible tilings all at once in a well-structured bag. That is where the true power of generating functions come in, considering everything all at once. If we are gonna solve this for each individual f of n, we would not have found this bizarre approach. Generating functions try to solve problems by considering a wider perspective, and somehow it works. Here's my favorite quote from mathematician George Pollier. A generating function is a device somewhat similar to a bag. Instead of carrying many little objects detachedly, which could be embarrassing, we put them all in a bag, and then we only have one object to carry, the bag. Now, let's apply our technique to count the lattice points. Although the reciprocity theorem applies for all polytopes, we'll simplify things a little bit by focusing on simplices, at least for this section. Basically, it is a multi-dimensional version of a triangle. So a one-dimensional simplex is a line segment, a two-dimensional simplex is a triangle, a three-dimensional simplex is a tetrahedron, and so forth. But for the sake of being able to draw on the screen, I will only focus on triangles in this section. But our method will apply for all the simplices. So, this will be our goal of this section. Given a triangle T in the plane, find the number of lattice points in n times t, which we will denote by f of n. To find what this function is, we will use the same technique that we used in the last section. Step 1. We will collect everything we want to count in a big bag and give it an algebraic structure. Step 2. We will think of an appropriate substitution so that the points belonging to the same dilated triangle will have the same symbol. After this step, we would have set up the following generating function. Next, we will try to evaluate this generating function in a different way so that we can find its coefficients. And after this, we will have our well-deserved formula for the number of lattice points in n times t. Okay, step 1. We are going to consider all possible positive integer dilations of our triangle and put all these points inside a bag. But wait, there's a problem. As you can see, since the triangles are overlapping, we would need to collect the points more than once. We can do that, but there is a better way. Okay, quick question. Can you see how to reposition our triangle T so that all of our dilated triangles are disjoint? It seems like no matter where you place your triangle on the plane, after some dilations, your triangles just became too large to be disjoint from one another. The answer is to think outside of the box. Just translate T by one unit in the z direction. This will put our triangle T onto the plane z equal to 1. And n times t will be on the plane z equal to n for each positive integer n. Therefore, this will make all of our triangles disjoint. And plus, this does not ruin the number of points in each dilated triangle, so we're good. With that, we're now ready to collect all these points into a bag, and let's name this collection as C. But here's one thing. We also include the origin in our collection, just like we included the empty tiling in the previous example. And with that, we are ready to move on to the second step. Just like we considered the tilings as products of x and y's, we want to associate an algebraic expression to each point in our collection. Each lattice point in our bag is a triplet of integers x, y, z, so we can associate it with the product p1 to the power of x, p2 to the power of y, p3 to the power of z. Here, p1, p2, and p3 are the indeterminates, and x, y, and z come from the coordinates of our point. And just like before, we will add up all such expressions as the point x, y, z ranges over all points in our collection. And we will call this resulting expression as sigma p of c. Here, remember, c is the points in our bag, and P is just a formal vector P1, P2, and P3, just to keep track of the variables. Okay, you formal folks might think it is weird because we are going to have negative numbers in our exponents. And yes, you're right, we need to be very careful with this. If you're feeling nervous about having negative exponents, you can try translating our triangle into the first octant. This will get rid of all the negative exponents, and hence putting our sigma of C into the ring of formal power series generated by P1, P2, and P3. Okay, back to the video. At this point, we have to look for a substitution in place of P1, P2, and P3 so that we can collect the terms representing the points of the same dilated triangle. How can we do that? Simple. Just let P1 and P2 to be 1 and P3 to be Z. Well, since each dilated triangle n times t lie in the plane z equal to n, this substitution will change all points in n times t into z to the power of n. Therefore, the coefficient of z to the power of n in the resulting sum will be the number of lattice points in n times t, which we denoted by f of n. We can write it concretely like this. Here, this 1 right here comes from the origin, whose corresponding expression is this. Also, from this perspective, we should just take f of 0 to be 1 just to make things easier to write. Okay, and with that, our second step is complete. So, on to the third step, which is to find this sigma in another way so that we can equate the coefficients and find f of n explicitly. Okay, before going into step 3, I want to simplify our notations a little bit. Suppose you have two lattice points a1, a2, a3 and b1, b2, b3. Here are their corresponding expressions if they were to appear in our bag. Okay, what happens if you multiply these products together? Well, you get this, which is the corresponding expression for the sum of our points. So, we can just abbreviate this notation like this. But in this notation, you can now more clearly see that when you multiply two expressions together, the exponents should add up. Okay, so this works perfectly fine with vector addition. And what about scalar multiplication? Well, same thing. If we have this expression correspond to this vector, then k times this vector is raising to the power of k. Again, the vector exponent notation makes this much more clear. So, with this convention, the look of our sigma changes from this to this, which is much more cleaner. Okay, we're ready to go on to step 3. We first need to notice that the points in our bag C actually forms the shape of a cone. In fact, if we let G1, G2, G3 be the vertices of our triangle, then C is the set of lattice points in the cone generated by non-negative combinations of these vertex vectors. Once you see it, you can also see that this entire cone can be tiled with copies of parallelepipeds generated by G1, G2, and G3. Whoa, does this look confusing? Well, let's take things easy and look at the 2D version first. Suppose we have two lattice points G1 and G2 on the plane, and consider the cone generated by non-negative combinations of these points. This is just the 2D analog of what we had previously. Now, it is at least more visually obvious that this cone can be tiled with the copies of parallelograms generated by G1 and G2. Notice here that our parallelogram does not contain the top and the right boundaries, because only then you can fill up the entire cone without overlap. Got it? It is the same thing for the 3D case. We can tile our cone with parallelepipeds generated by G1, G2, and G3, while the faces not containing the origin are removed, so that we can tile the entire cone without overlaps. So, how does this tiling even help us to decompose our sigma? A lot. Actually, we already got everything we need. All we need to do now is to write down this tiling with parallelepipeds idea in terms of algebra. Okay, we will do the 2D case first to make things simple. Consider the following two collections of lattice points. First is the collection of lattice points in our base parallelogram P. And the second is the collection of lattice points in our grid G, generated by the non-negative integer combinations of G1 and G2. So algebraically, these collections are sigma of P and sigma of G respectively. So it means that we are just adding up the expressions in P and adding up the expressions in G. I claim that the sigma of the cone is the product of these sigmas of P and G. You can actually see why by just staring at the expression long enough. I swear that works. But here is a nice way to put it. Since we can tile our cone by putting the base of the parallelograms P at each point of G, every point in our cone is the sum of a unique point from P and a unique point from G. Therefore, sigma of our cone is sum of all P to the power of vector A plus vector B, where vector A is from the parallelogram and vector B is from the grid. In other words, it is just the sum of all possible pairs of products taken from our sigma of P and the sigma of G. Hence, this is just the product sigma P times sigma G. In a similar way, we can further decompose the sigma of G. Can you see the sigma of what and the sigma of what multiplies to give you the sigma of G? Well, each point in G is the sum of a unique point from this yellow set and a unique point from this red set. Therefore, sigma of G further decomposes into the product of sigmas of yellow set and the red set. Now, what is the sigma of the yellow set? Right, it is just the collection of all multiples of G1. And similarly, the red set is just the collection of all multiples of G2. Therefore, they look like this. Familiar? Of course, these are just geometric series, so we can add them up like this. Hence, our sigma of the original 2D version of the cone equal to this expression. Now, if we go back to the 3D space, we can do the exact same thing. First, we decompose the sigma of the 3D cone into the sigma of the parallelepiped and the sigma of the grid. Now, the grid is the product of 3 sigmas, one for each vector Gi. So, we can write the sigma of the 3D cone like this. Neat, right? We just got another way to write our sigmas. Now all we have to do is to substitute P1 and P2 to be 1 and P3 to be Z. What will happen to this guy if we substitute P1 and P2 to be 1 and P3 to be Z? Well, the x and y coordinates will disappear, and we will be left with z to the power of the z coordinate. But since our triangle lives in the plane z equal to 1, this is just equal to z. So what about the numerator? Well, what happens to the sigma of the parallelepiped? Well, it just becomes some polynomial of z. And to be exact, it is actually a quadratic polynomial of z. So, there we go. We have finally found the generating function for f of n. The exact formula would depend on the sigma of our parallelepiped, which kind of makes sense, since that parallelepiped could really be anything depending on our choice of triangle. Now, to cool off our brains a little bit, let's do an example. Consider the following triangle with vertices as shown. As usual, let f of n be the number of lattice points in n times this triangle. We can use the formula we just obtained to get the formula for the generating function of f of n. Well, we first need to know the lattice points in our corresponding parallelepiped, which in this case turns out to be these guys. And upon substituting p1 and p2 to be 1 and p3 to be z, we get this. And there we go. We have our generating function for f of n. Now that we know this exactly, we can actually compute the explicit formula for f of n. Again, this is just a standard computation if you are familiar with Taylor series stuff in calculus. So there we go. A nice simple formula to calculate the number of lattice points in the nth dilate of the triangle. And if we want to experiment with a few more triangles, we will get the following f of n's. You can notice some things here. For example, they are all polynomials of degree 2, and all of their constant terms are equal to 1. These are indeed all true for every triangle, and you can figure it out just by playing around with our generating function. A somewhat surprising fact would be that these leading coefficients are the areas of the corresponding triangles. And these polynomials are called Ehrhart polynomials, and all of the things we did, including the facts that I just said, are true for the d-dimensional simplexes. Okay, that's enough facts for now. Let's go back to the general theory of generating functions. Okay, in this section, we'll go through what is meant by substituting negative numbers, and how they're related to generating functions. The phrase substituting negative numbers isn't as simple as it sounds. Look at these two formulas. For all positive integers n, these two formulas are the same. However, if we substitute negative integer negative n, then f of negative n is 3 minus n cubed, while g of negative n is n cubed plus 3. Therefore, we cannot simply say substitute negative numbers into the formula. depending on the formula, this can have different meanings. So then, given a sequence A0, A1, A2, and so on, how do we define A-1, A-2, and so on? To motivate this, let's go back to how we define negative exponents back in the middle school or high school, depending on where you live. For a positive integer n, we all know what 2 to the power of n means. Just 2 times 2 times 2 times 2 times 2 up to n times. But this does not make sense if n is a negative number or even 0. I mean, what even is multiplying 2 for, let's say, -1 times? It does not make sense. But however, we somehow managed to define 2 to the power of non-positive numbers. And the way we did that is what I like to call continuing the pattern. If we look at the sequence of positive powers of 2, we can see a pattern. Well, the pattern is this. To get the next power, we multiply the previous power by 2. Or equivalently, we can say that to get the previous power, we divide the next by 2. If we wish to continue this pattern, then we must define 2 to the power of 0 as 2 to the power of 1 divided by 2, which is equal to 1. And similarly, we must define 2 to the power of -1 as 2 to the power of 0 divided by 2, which is a half, and so on. We can use the same technique for the general sequences. Well, not all sequences, but a large family of sequences. So, given a sequence A0, A1, A2, and so on, what we do is we first find a pattern among the non-negative terms. For this video, the pattern that we are going to talk about is called linear homogeneous recursion. Don't get scared. Ready? It looks something like this. Where d is a fixed positive integer and c0 to cd are constants with c0 and cd not equal to 0. Whoa, looks intimidating. But this just means that the next term an is equal to the linear combination of the previous terms an minus 1 to an minus t. In our previous example of the 2 to the power of n sequence, we had this pattern, which is the linear recurrence relation. Well, it turns out that such a recurrence is unique if we chose d to be as small as possible. So it means that we can simply extend our pattern into negative numbers in a unique way. So, our plan for this section will go in 2 subsections. 1. We will establish the relation between linear recurrences and the generating functions. And 2, we'll find out what happens to our generating function as we continue the terms into negative numbers. Okay, subsection 1, let's begin. Recall the problem that we did 2 sections ago. This guy, remember? F of n counts the number of tilings of 1 by n rectangle using identical 1 by 1 rectangles and 1 by 2 rectangles. To extend this to negative numbers, the first step is to find the linear recurrence. Let's see. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and the pattern continues. So, the recurrence relation for this sequence should be this. To get the next term, we simply add up the 2 previous terms. But why is this formula true? Well, you can prove it with just simple counting, but since we already know its generating function, we can do it much easily now. Recall that the generating function of f of n is this. So, if we move things around, we get this. By expanding the product on the left, we can find out how the f of n's are related. So, let's expand. For n at least 2, the coefficient of z to the power of n on the left side is this. And on the right side is 0. Therefore, we have proved the promised pattern. To get the next term, you just add up the two previous terms. Okay, what about the coefficients of z to the power of 1 and the constant term? We get the following relations, which is equivalent of saying that f of 0 and f of 1 are both equal to 1. This works in general whenever our generating function is the ratio of two polynomials with the degree of the numerator less than the degree of the denominator. Let's call these proper rational generating functions. To convince you a little bit more, we will look into a more complicated example. Suppose that our mysterious counting sequence have this giant generating function. Using the same technique, we can recover all the terms in our sequence. We first rearrange and then expand. For n greater than or equal to 4, the coefficient of z to the power of n is this. And since the degree of the right side is less than 4, this coefficient will always be 0, and hence giving us the linear recurrence relation. For n less than 4, the coefficient of z to the power of n are the following. And so, we have these relations. Therefore, a0 is 1, and this gives us a1 is equal to negative 1, and so a2 is 5, and so a3 is negative 15. Thus, just by using the proper rational generating functions, we have recovered both the initial conditions and the linear recurrence of our mystery sequence. Looking more closely, we could see that the denominator completely determines the linear recurrence of the sequence, and the numerator completely determines its initial conditions. The relation between the denominator and the recurrence itself is also very easy to remember. Look, to get the recurrence, we just need to read off the coefficients of the denominator from left to right and stick them up as the coefficients of our recurrence. Now, it is quite obvious that this trick will work in general. So, we have constructed the correspondence between the sequences with linear recurrences and the proper rational generating functions. The denominator always uniquely determines what the linear recurrence is with an easy rule to remember, and the numerator always uniquely determines the initial conditions. Wait, why are we doing this again? Oh yeah, substituting negative numbers. So, our next step would be to extend the recurrence into the negatives and see how it changes our generating function. Let's try to extend the sequence that we used in the previous example into negative numbers. The generating function for the sequence upstairs is which we already know the formula of, and the generating function for the sequence downstairs is this, and we want to find the formula for this guy. Okay, I would cheat a little bit here. It turns out that the resulting formula is super nice if we start the bottom sequence with a negative 1 instead of a0, and so we are adding from n equal to 1 to infinity instead of n equal to 0 to infinity. This little fix does not matter that much, since we can simply recover the original bottom sequence by adding a0 back in. Okay, time to evaluate. Since we defined the bottom sequence by extending the recurrence of the upstairs sequence, the bottom sequence also has a linear recurrence relation. Therefore, we can guess that the formula for its generating function is also rational proper generating function. The denominator is easier to get since we already know an easy way of associating denominators with linear recurrences. Let's take a look. This is the recurrence relation for the upstairs sequence, obtained by reading off the coefficients of the corresponding denominator. So the recurrence for the downstairs sequence is the exact same recurrence, but the direction of the sequence is reversed. In the upstairs sequence, n is the next term and all the other terms are the previous terms. But in the downstairs sequence, n minus 4 is the next term and all the other terms are the previous terms. And therefore, the corresponding denominator is obtained by reversing the order of coefficients in the upstairs denominator. But reversing the order of coefficients can easily be captured with a single substitution. If we denote the denominator of the upstairs by q of z, then the denominator of the downstairs is q of what? Take a second to think. Got it? The answer is q of 1 over z. You see, by substituting 1 over z in place of z, the largest power becomes the smallest, and the smallest power becomes the largest, thereby reversing the order of coefficients. Well, I cheated a little bit. The correct answer should be z to the power of 4 times q of 1 over z, since we need to have a polynomial in the end. So, let's recap. Given a sequence with a linear recurrence, we construct another sequence by continuing the recurrence. If we denote the corresponding generating function for the upstairs sequence by pz over qz, then the denominator of the corresponding generating function in the downstairs is equal to z to the power of d times q of 1 over z, where d is the degree of the denominator. What about the numerator? Luckily, thanks to our fix by dropping a0, the numerator turns out to be this guy. So, the z to the power of d's cancel out, and we're left with this beautiful relation. We can make it even more concrete by writing the upstairs generating function as big F of z, and then the downstairs generating function is just negative big F of 1 over z. A very elegant and a short formula. Okay, for those of you who are feeling ticklish for me not explaining why the numerator is very nice, I encourage you to prove it by yourself. Just jot down some coefficients and you'll see what's happening. Okay, now that we have all that prepared, we are finally ready to fill in the missing piece. 2 sections ago, we proved this. Here, f of n is the number of lattice points in n times t, where t is some lattice triangle. Now, what we are going to do is we let g of n be the number of lattice points in the interior of nt, and find the corresponding generating function for g of n. The way we're going to do this is exactly the same as the way we did for f of n. First, let's lift up t in the z direction by 1 unit. And then consider the cone generated by its vertices. Now, since we are only going to consider the points that are strictly inside the triangles, we need to remove the boundary of the cone. And so, let's call this skinless cone as C interior. Just like before, we are going to consider the sigma of C interior, which is just the sum of the algebraic expressions corresponding to each point in our C interior. Now, to get the generating function for g of n from this sigma, we can also do the same thing, which is to substitute p1 and p2 to be 1 and p3 to be z. Now it is time to decompose the sigma. Again, to make things simple, we'll look at the 2D case first. Previously, we managed to decompose the sigma of C by tiling it with copies of this parallelogram P. But this does not work for C interior because of the inclusion of these two edges. Or at least if we are trying to tile in this way. Here's another quick question. Can you see a way how we can use these parallelograms to tile the interior of the two-dimensional cone. The answer is to rotate our tile by 180 degrees first. Then we can easily tile the interior like this. We will call this rotated parallelogram as negative p. And this notation makes sense since we get negative p by reflecting every single point of p about the origin. So, our two-dimensional cone can be created by putting the copies of negative p at each point in this red grid. And hence, the sigma of the interior of the two-dimensional cone can be decomposed as the product of the sigma of negative p and the sigma of this shifted red grid. Got it? Then we can further decompose the shifted grid like this. Now, all we need to do is to simplify these things. Let's watch. And there we go. We have obtained the sigma for the interior of our cone. And if we do the same thing for the three-dimensional cone, we will end up with this. Does this look familiar? Here, take a look at what we have obtained in the previous section. The only difference between the sigma of the three-dimensional cone and its interior is that the sigma on the numerator is of negative p instead of p, and in the denominator, we have p to the power of negative g instead of p to the power of g. So, what is the relationship between sigma of negative p and sigma of p? Well, since the points in negative p are obtained by reflecting each point of p at the origin, for each term in sigma of p, this will be their corresponding term in negative p. Or in other words, we can obtain the sigma of negative p by replacing each variable with its reciprocal in the sigma of p. Okay, that takes care of the sigmas. Now, what about the relationship between these two guys? This one is much more easier to see. Just take a look. So, we can get the sigma of the interior of our cone simply by substituting each variable with its reciprocal. And so, when we plug in p1 and p2 to be 1 and p3 to be z, the corresponding generating functions will have the same relationship. That is, if we let the generating function of the top sequence with capital F of z, and then the generating function for this bottom sequence will be negative capital F of 1 over z. And according to what we just proved, this means that f of negative n counts the number of lattice points in the interior of our triangle. And just like that, our proof is complete. For the d-dimensional simplexes, since we are going to have d plus 1 vertices in our simplex, the sigma for the corresponding cone looks like this. And so, this is the sigma of its interior. And if we rearrange things a little bit, we will get this. So, after substituting z for the last variable and 1 for all the other variables, we will have this. These negatives are kind of annoying, but we can get rid of them by just multiplying both sides with negative 1 to the power of d. And this puts our formula in the same format as we had in our previous section. And so f of negative n actually counts -1 to the power of d times g of n. Or in other words, f of negative n is just the number of points in the interior of n times t times -1 to the power of d. And there we go. We have proved the Ehrhart Macdonald reciprocity for all the simplices. So what about general polytopes? Well, as usual, we can see the 2D case first. We'll illustrate our argument with this polygon in the picture, but this method will work for general polygons in the plane. But for this one, I think it will be better for me if I don't say anything, and I'll just let you watch what happens. And there we go. What we have here on the right side is the number of points in the interior of n times p. So our proof is complete. But unfortunately, this method that we used for the polygons is not generalizable to the general polytopes. The point where it fails is at triangulation. General polytopes cannot be decomposed into simplices that easily. Well, I'm not saying it is impossible, but the tools needed for making this work are just too much for the scope of this video, which is supposed to be dedicated to generating functions. Hey guys, if you made it to this point, first of all, congratulations and thank you. Making this video has been in the back of my mind for a while, ever since I encountered the idea of spraying an algebraic expression over the object that we are counting to get a generating function. This really changed the way I think about generating functions, and I really encourage you to go back to your favorite generating function problem and try to think about it from this perspective. And there is one thing that I want to admit here is that I hand-waved over a lot of details in my video. Some of them that I tell you explicitly that I skipped, and there are some others that I did not. If you can spot them, make sure to leave them in the comments. And if you want to experience a non-hand-wavy version, I recommend you this book. It's called Combinatorial Reciprocity Theorem, an invitation to enumerative geometry combinatorics, written by these two authors. It's a really good book, so make sure to check it out if you're interested in this video. Oh, by the way, when I was working on this video, I saw someone already made a video on the first chapter of this book, so if I can find the link, I'll leave it in the description. And yeah, that's about it. Thank you so much to Grant and James for hosting this Summer of Math Exposition. This really helped me with my motivation to put this video together. And yeah, see you guys in the next video.